You're about to meet your first non-Euclidean geometry. It's spherical geometry, which you can think of as the geometry of the Earth's surface. And what we're going to conclude is that with one small exception, Euclid's first four postulates hold just fine in spherical geometry, and the fifth postulate fails miserably. This means that almost all of the first 26 propositions in Book 1 of Euclid are going to be valid in this geometry, and Euclid's proofs of them will be valid also. I get to pick a unit of length, and I'm going to choose a unit of length equal to the radius of the Earth and assume that the Earth is a perfect sphere. The lines of our geometry are going to be great circles, and great circles, of course, intersect in two antipodal points. We'll solve that problem by considering only points on the Earth's surface that are in the part of the world known to the great geographer Strabo. That's Europe, North Africa, nearby parts of Asia. These are, for the most part, east of Greenwich, England, so the latitude will be positive because they're north of the equator, and the longitude will be between 0 and 90 degrees because they're in the eastern hemisphere. But we can also consider locations in the western hemisphere. Gibraltar, for example, is at 5 west longitude, and on rare occasions we will even consider the New World. So here we have a three-dimensional model of a non-Euclidean plane geometry. But it's a plane geometry because all the points lie on a surface in what's technically called a two-dimensional manifold, the unit sphere. And the main problem with representing this geometry on paper is that it's hard to represent the sphere in a Euclidean plane. Over the centuries, map makers have devised a lot of ingenious solutions to this problem. One of them is the Mercator projection, which is used for the Student Locations tab in Canvas. As I said, lines in this geometry are great circles. Line segments are portions of great circles, and it's easy to find the line segment from point A to point B. Just get a globe, stretch a string tightly between point A and point B, and that string will specify an arc of the great circle. That is the shortest route between the 2 points. Skilled navigators are pretty good at figuring these out. When you fly from the eastern U.S. to Europe, for example, you go way far north because you're following a great circle route. Meridians of longitude, lines of constant longitude, are lines of spherical geometry. They start at the North Pole and go down to the South Pole. Parallels of latitude, where the latitude is constant, are not lines. They're circles, okay, with the center at the North Pole, and you can also characterize them as so-called equidistant curves relative to the equator, which is a line, in the sense that the distance from a parallel of latitude to the equator along a meridian of longitude is the same at every longitude. If you read Strabo, it's not at all clear that Strabo understands that a parallel of latitude is not a straight line in the sense that it's not the shortest route between 2 points. If at the latitude of ancient Greece you keep walking due east, you are not traveling along the shortest route to the point where you will eventually end up. Now let's get a little more formal about this. We are going to specify a point the way geographers do by means of 2 angles. The longitude is measured around the Earth in radians. It can be as negative as minus pi radians. It can be as positive as plus pi radians, but we will never consider longitudes that exceed pi over 2 in magnitude. The longitude is 0 at the Royal Observatory in Greenwich, England, and roughly 0 in Accra, the capital of Ghana. The longitude goes up to pi over 2, somewhere around Kathmandu, and you can go slightly into the Midwest in the United States before the longitude becomes less than minus pi over 2. We measure latitude north from the equator, so in the northern hemisphere, the latitude, which is 0 at the equator, goes up to pi over 2 at the North Pole. And now we can write the three-component vector that represents a point with a specified longitude and latitude. This is very important. We're going to be using it over and over again, and we'll use something very similar with hyperbolic functions when we do hyperbolic geometry. The z-coordinate, measured north up from the equatorial plane, is equal to the sine of the latitude. Starts at 0 at the equator, goes up to 1 at the North Pole, down to -1 at the South Pole. At latitude phi, the radius of a circle around the Earth is no longer 1 as it is at the equator. It's dropped down to cosine phi. And when we take a point on that circle, as is conventional in polar coordinates, multiplying by the cosine of the longitude gives us the x component, multiplying by the sine of the longitude gives us the y component. What about lines? Well, as I said, a line is a great circle on the sphere. You can think of it as the intersection of the sphere with a plane through the origin, through the center of the Earth. Given any such plane, you can construct a vector perpendicular to the plane. You can make that into a unit vector, and the conventional term for this is the unit normal to the plane. That lets us describe a line alternatively as the set of all unit vectors that are perpendicular to a certain pole. The terminology: this vector is called the pole of the line, and the line itself is the polar line of the pole vector. There's a slight complication here, of course. If n is a pole for a line, for example, the vector that points straight up through the North Pole is the pole for the equator, but so is -n, the vector that points straight down through the South Pole. What we will do is to choose the pole so that the third component, the z component, is in the northern hemisphere or, on rare occasions, on the equator. If you traverse a line in an easterly direction, or if it's a north-south line, if you traverse it in a northerly direction, then your right-hand thumb will point in the direction of the pole that we'll be using. Now, remember how we successfully parametrized a circle in the plane. This is also going to work in exactly the same way for a line of spherical geometry. So the circle in this diagram can be thought of a great circle anywhere on the Earth. And we have a point P, a position vector that goes from the center of the Earth out to P. That has unit length because we're thinking of a unit sphere. And then we have a direction vector, V, that's tangent to the circle, tangent to the surface of the Earth, along the line that goes from P to Q. And you will recall that given any angle, S, if you take the direction vector and multiply it by the cosine of S, add on, sorry, I said that wrong, the position vector times the cosine of S, plus the direction vector times the sine of S, you get another point, Q, on the same circle. It's a function of the angle S between these two vectors that you chose. What about constructing the line that joins two points? Well, there are two ways of doing this. If you've ever studied physics, you probably learned about the cross product of two vectors. If you have 2 points P and Q with spherical geometry, their cross product points perpendicular to both of them, And since these points lie on a certain line, their cross product is perpendicular to that. The only problem is usually P cross Q is not a unit vector. Easy fix, we divide it by its own length. So this is a convenient way of constructing the entire line on which points P and Q lie. It's not a particularly good way of constructing just the segment from P to Q, which is what we're usually going to want to do. So here's a better way. We can figure out the distance between points P and Q by exploiting the dot product, which you may have met in a math course, you may have met in a physics course. The dot product of two vectors is the product of their lengths times the cosine of the angle between them. And for unit vectors, the dot product is just the cosine of the angle. So I can say the distance from P to Q is the arc cosine of the dot product P dot Q. Hey, you said you were going to define distance and now you're talking about angles. Well, that is the way to measure distance in spherical geometry. Imagine yourself sailing across the Pacific Ocean on the equator. You can go a long way on the equator in the Pacific Ocean. How far did we get today? Oh, we covered 2 degrees today. The natural way of measuring your progress along the equator is to measure your increase or decrease in longitude in degrees, and the same thing works quite generally. If we know the angle between the vectors P and Q for 2 points, we know the great circle distance between those 2 points. And this gives us the parametric method of constructing a line. You'll see a lot of examples of this in R, and you'll see that all we have to do is replace ordinary trig functions by hyperbolic functions, and this will work equally well in hyperbolic geometry. So we want the line segment from P to Q. First thing we do is we calculate the distance in radians from P to Q, and we know that Q is therefore the position vector P times the cosine of that distance plus the direction vector V times the sine of that distance, and we can solve this equation for V. Q minus P cosine of the distance divided by the sine of the distance. And then, once we got both the position vector and the direction vector, we can construct points on the segment from P to Q by just using different values for the distance, S, in between 0 and D. Finally, we're ready to look at Euclid's first 4 postulates. The first one says I can construct a line given 2 distinct points, and indeed 2 distinct points P and Q determine a line, but that line is not a straight line in 3-dimensional geometry, it's a great circle on the Earth's surface. Second postulate, a line can be extended as far as you like in either direction. Well, that's certainly not quite true in spherical geometry. If you give me a line segment, for example, the great circle route from Athens to Persepolis, I can extend that west of Athens, I can extend it east of Persepolis, but there's a limit to how far I can go. If I extend the segment so that its length becomes greater than pi radians, so that it goes halfway or more around the Earth, then the shortest way back to my starting point is to go round the backside of the Earth. So as long as proofs do not require extending a line so that its length becomes more than half the circumference of the Earth, Euclid's proofs are valid. Euclid proposition 16, which says that an exterior angle of a triangle is always greater than either interior angle, is not true in spherical geometry. The easy counterexample is a triangle that has 3 right angles, 1 at the North Pole and 2 on the equator. But if you look carefully at the proof, you'll discover that Euclid requires that you extend the side of a triangle to twice its original length. And if the triangle is too big, you can't do that. Postulate 3 holds just fine, and in fact, with an ordinary compass and a globe, you can stick the point of the compass down into the globe, draw a circle, and it works just the same way as in Euclidean geometry. Right angles exist, and a form of right angle that's easy to visualize is take the equator, cut it with a meridian of longitude, the angle on either side is the same. That's Euclid's characterization of a right angle. And to justify the statement that all right angles are equal, I can point out, you give me a right angle anywhere on the globe, I can rotate the globe so that the right angle is at the topmost point, formerly occupied by the North Pole, and I can even put the two arms of the angle along the x-axis and the y-axis respectively. So by rotating the sphere, I can map one right angle onto any other. So far, so good. What about the fifth postulate? Well, remarkably, as Euclid states it, it actually holds, because what does Euclid say? He says, take a line, it'll be the equator, that cuts two other lines. These are two meridians of longitude. And the two lines that it cuts are the prime meridian, and then instead of using a meridian here, we'll use this line drawn in red that makes an angle less than 60 degrees. Euclid's fifth postulate says if the sum of these two angles is less than two right angles, that is less than 180 degrees, the lines will meet on this side. That's true. Euclid never bothers to say if the sum is exactly two right angles, the lines will never meet because they're parallel. He clearly implies that, and that's not true in spherical geometry. If I change this angle from 60 degrees to 90 degrees, these meridians still meet at the North Pole. Lots of theorems in Euclid involve rectangles, squares, and other parallelograms. In spherical geometry, because there are no parallel lines, these geometric objects don't exist. Strabo, you'll discover, characterizes certain geographical regions like Macedonia as being in the shape of a parallelogram, but there are no parallelograms in spherical geometry. Now remember common notions? In the version of the common notions where there are 9 of them, the ninth one is two lines cannot enclose an area. And if you consider two different meridians, this one and that one, from the North Pole to the South Pole, they certainly enclose an area. They enclose a portion of the Earth's surface. So not only does the fifth postulate fail, the ninth common notion also fails in spherical geometry. So let's sum up our conclusions. As long as we use only the first 4 postulates and don't try to extend a line so that its length exceeds half the circumference of the Earth, spherical geometry is a model that satisfies Euclid's first 4 postulates. And the proofs for propositions like constructing an equilateral triangle, as you will see, work equally well in spherical geometry. You will soon meet the spherical toolkit that looks a lot like the Euclidean toolkit, except that it does spherical instead of Euclidean geometry. If there are well-known facts of Euclidean plane geometry that aren't true in spherical geometry, for example, the Pythagorean theorem, or the statement that in an equilateral triangle, each angle is a 60-degree angle. Or more generally, the fact that in any triangle the angles sum to 180 degrees. None of these things is true in spherical geometry, and that means that Euclid's proof somehow or other either requires the fifth postulate, requires parallel lines, even if there's no evidence of parallel lines in the actual statement, or on occasion, Euclid's proof works only if a line is extended so far that in spherical geometry it could exceed pi radians. Okay, with that brief introduction, you'll be ready to meet a detailed discussion of spherical geometry in R, and you will soon be constructing lines and circles in this geometry.